Hi, everyone. Thank you for joining today. Because we're expecting a much larger group, we're going to have everyone muted for the time being. But if you do have a question, please feel free to raise your hand. We'll get to your question or just message in chat. And we do have a Q&A session at the end too, if you have any other questions. So just wait for a bit more people to join in before we get started. Okay, yeah, I think we'll get started now. So thank you for coming to joining today's session on hybrid heat pumps and heat recovery systems. We'll have Shahryar be our main expertise today, presenting the topic. And on the next slide, you can see is Save on Energy Managers Playbook is a podcast. It's available on Apple Music, Amazon, and Spotify. It's a quick 15 to 20-minute listen, and it discusses like real world stories on the energy management community and challenges that we're facing in the industry as well. So if you do have any time, for a quick 15-minute car ride, have a listen at the Energy Managers Playbook podcast. So with that being said, I'll pass on to Sharia.
Thank you so much for the introduction. Welcome, everyone. I guess that if you're in Ontario, so good morning, everyone. We have a nice weather. Still is warm in October. So today, as you saw in the title, we are going to talk about the heat pump systems and typically the hybrid heat pumps, the fundamentals and the basics about that one, and also very briefly review heat recovery because heat recovery is also a broad topic actually in mechanical engineering itself. And then we look at some kind of optimization strategies, especially with the controls. And then I'm going to present a couple of case studies that actually integrated these two systems together. So getting heat pump and heat recovery together and then benefit or increase the benefit of both of these systems actually. So that's the agenda for today. Hopefully I finish it, before the end of the hour, and then, we can have a Q&A at the end of our session. The goals for today is that we want to understand the basics and principles of a heat pump and heat recovery. We want to review the common types of both of these systems that they exist, looking at the control and optimization strategy, to improve the performance of, again, both systems, and then see the real world, see the engineering real world, that how they use both of these systems in an efficient way actually, and then what are the strategies that we can see from the applications that are available right now to us actually. But I mean, as an introduction, let's start with a big picture and see that what's happening around us actually. So why heat pumps and heat recovery? I mean, the first reason is that in a building sector, we basically use about 30 to 40% of energy actually. So the heating and cooling, they use 40% of the energy actually of a building. I will show you some graphs, in the next slides actually for Ontario. Then the idea is that now, after we complete our energy study and then we complete our energy conservation, the next step in a energy hierarchy or energy management hierarchy for us is that to look at the energy efficiency. So now we want to bring a more efficient system actually. So how we can do that one? Heat pump is one of the solutions. Heat pump, I will show you later on, is more efficient than the other system. The other one is that there are many waste energy sources or waste heat energy sources available within our processes and our buildings. And it's better that we capture them actually because we spend energy for them. We paid for that. Now it's better that to recover them, reuse them, and then increase the overall efficiency of the system. So the key message of both of these systems is that both of them improve the efficiency. So they are designed for improving the efficiency. At the same time, we want to reduce the utility cost, so the energy cost that we have, and also decarbonization, reducing the GHG emissions from the heating and cooling for our buildings, actually. Let's look at Ontario and energy sources. So this is for Ontario. I mean, I see this is it might look an odd, unit. It's a petajoules, but 1 petajoules equals to 10 to power 15 joules, or 200, let's say 80 gigawatt hour. So if you want to just roughly convert it, multiply any numbers that you see on a vertical access to 280, and then you get, the gigawatt hour of energy actually. But I mean, the most important thing for us is that we see natural gas in the residential sector is the main energy use, actually, the energy type that we use. After that, it comes electricity. So this is for the residential sector. For commercial and institutional sector, it's slightly different. But again, natural gas is number one for us. And then number two is the electricity. So these yellowish color, that you see in the bars, that's the natural gas consumption actually in commercial and institutional sector. And after that, um, electricity. Then it becomes obvious the GHG emission from these sources. Again, natural gas has a higher emission factor compared to electricity, especially for us. We are lucky we live in Ontario, and this is a proof that what's happened in Ontario for our electricity. Thanks to ISO, thanks to OPG, that they closed down all the coal power plants, and now our electricity is fairly green actually, and less carbon intensive compared to the other provinces actually. So that's a good thing, but still natural gas is a fossil fuel and it emits a lot of greenhouse gases actually. So we need to do something about that one. And the same for the commercial and institutional buildings. Again, the same graphs that you see, emissions for natural gas, the other reason is that the electricity portion is fairly small, and that's why I make the natural gas, a bold emission, from our buildings actually. The next thing that I have for you is that, so it's obvious that where we use natural gas, and also our climate also tells us that where, but just to confirm that one, again, space heating, that's the number one end use that we use natural gas in residential building, and again, space heating in commercial and institutional buildings, again, is the responsible section of our buildings or mechanical systems in our building that use energy actually. So that's the one thing. The second that you see here, which is in the blue color in here, that's the water heating. Again, we use fossil fuel, and fossil fuel, it comes for residential building. For the commercial building, they don't use that much, water heating. They exist. You see a very narrow band of yellow strip in here, but then the other ones like auxiliary and other end users actually, they play a bigger role. But again, space heating. Let's now look at the emission by the end users actually, and then you see we have almost around 10 to 15 million tons of CO2 for residential every year goes for space heating. That's the emission that we have. And then almost less than that for commercial building. It's around 10, again, 12 to 14 million tons of CO2 emissions for commercial and institutional sector. So all these data, I took them from Natural Resources Canada, NRCan, and they publish those data. They are available. Feel free to go to these data and use it for your studies that you want to do actually. And the last one that I want to show you is the space heating and water heating, again, in Ontario, and the amount of energy that we use is around 400, it's around 300 to 400 petajoules, which is around 100,000 gigawatt hour of energy that we use. For commercial building is less, it's around 250 to 300. Again, it's in the ballpark of 90,000 to 100,000 gigawatt hour of energy that we use for space heating and water heating in Ontario. And then you see the trend is not that much. We see a drop from 2015 to 2016, but the trend is almost, look at the recent, especially the recent years like 2022, we see the same amount of energy use or emissions actually. I tried to find a most recent version of this graph, but the only data that I got is here. It said in 2020, 5, I'm in Ontario, saw 100,000 installation of a heat pumps actually. So this is good. And the only thing that in this graph that we see here, it's a big trend, especially for Ontario, which is the yellow one. We see an increase actually in the installation of the heat pump. So this goes to 2016. I couldn't find anything after that one, but I imagine and I assume that it's the same trend, and we see more and more installation because of incentive and because of the efficiency of the equipments actually. So this slide shows us that we use fossil fuel. Still, we use fossil fuel for space heating, for water heating. I know that natural gas is still is cheaper than electricity, but let's look at the heat pump and let's compare them together and see that isn't it a good idea to switch to heat pump or not? So a basic definition of a heat pump: heat pump is a mechanical device that actually transfers heat. So the objective or the work that this equipment that you see here is doing is transferring heat from a source to a sink, or rejected to a sink. This source and sink can be air, can be ground, can be water, can be waste heat, and so on actually. The primary use of heat pumps is for space heating, space cooling, and also water heating as well. So, I mean, it fits with, so the technology is well advanced for our mechanical system. But as I talked before, let's compare these systems together, side by side, and see that, do we see a big difference or not? If we have a combustion unit, like a furnace, like a boiler actually, the energy cost for us is around $15 per gigajoule. So it's better that we use the same unit. So then it's going to be an apple to apple comparison for us. If we just install a resistance heating system like this baseboard that you see here, the cost of heating or the energy cost becomes $41 per each gigajoules actually. So this is super expensive. So I mean, maybe, I mean, the best wording is that it's not a good idea. This is super expensive. It doesn't make sense. $15 versus $41 is almost three times more expensive. So forget this system. But what about the heat pump for heating and cooling actually? If you include the efficiency or the COP, coefficient of performance, because these units, they don't have the direct efficiency because the heat is getting transferred, but electricity is provided to them. That's why we need to use COP actually. But if we use COP of 2 or 2.5, then the price or the energy cost becomes $10 to $20 per gigajoule. This is comparable to the $15 that we have for natural gas. One of the reasons is that natural gas burning systems, they are not that efficient. They are in the range of, if they are, brand new systems, their efficiency is going between 80 to 92 to 3% actually. If they are condensing units, so for sure, they are going to be above 90%. If they are non-condensing, which I don't think that anybody buy those ones, but still they are available, they are cheaper, so their efficiency goes down to 80% range. So if we include that efficiency, then we will see the price they become, or the cost of energy or utility for us becomes comparable. So that's a good sign of using the heat pumps. The other thing is the emissions. The emission of a combustion system or fossil fuel burning heating system, it's around 50 kilogram CO2 per each gigajoule of energy used. We said that forget the electricity, although electricity in Ontario is very, very green. So that is equal to almost 8 kilograms CO2 per each gigajoule of energy electricity used. But look at the heat pump. Because of the high COP, the emission from a heat pump, it's going to be around 2 to 4 kilograms CO2 per each gigajoule. I just want to add to this one is that even for cooling, it makes it better because it's more efficient. Sometimes it's more efficient than the existing air conditioning systems that we have. So we need to consider that one. So emission reduction, a large emission reduction, and the cost of utility becomes comparable. So that's the message from this slide. But let's look at all the advantages, and then I have the disadvantages in another slide. So it's not all positive things. I know that it's not a perfect thing, but energy efficiency, that's the number one for us actually. So why we should choose heat pumps, I showed you in the previous slide, but the heat pumps, their COP is 2 to 4 actually. So it means that if we want to, you know, if the mechanical engineers, they don't listen, we convert it to efficiency, it's going to be 200 to 400 times efficiency versus the combustion equipments, they have efficiency less than 90, 95%. So that's number one. The second one, heat pumps, they provide both heating and cooling, which is, this is a good, another, good that we can use it. It's a one single unit instead of having one air conditioning or chiller or another unit, one for cooling or for one for heating. We have one unit and it can benefit for that one. Environmental benefits, you saw it with the numbers that I presented in the previous slide. So that's the third one for us actually. The other one is the safety, improved safety that we have because inside the building now we don't have a combustion, we don't have fire, we don't have flame. So then it becomes cleaner and much, much more safer actually. So monoxide, carbon dioxide, and those gases are not going to come to our buildings and then increase the hazard and unsafe environment. They have a better comfort if they are designed actually in a proper way, so they can provide a better thermal, especially thermal comfort rather than the other systems that we use. They can last longer. So if they are well maintained, so they can last longer. And the other thing is that the zone control. So, I mean, if we go to an advanced heat pumps systems, so even we can provide heating and cooling at the same time, depending on the zone's demands, actually. Maybe one area they want heating, the other area they want cooling. The heat pumps, they are capable of doing that one, actually. What are the sources of the heat pumps? The heat pumps are actually categorized based on the source. So one way is that look at what is the source for the heat pump. Typical ones that you see in this picture as well, they are air source heat pumps. We install it outside and then they either take the heat in a winter season from outdoor air and then pump it in to the building, or in a summer season, they actually take the heat from indoor environment or inside of the building and then pump it out. So that's an air source heat pump. That's air to air heat pumps actually. The other one is a water source heat pump, means that now I will have a couple of slides for these ones because I mean, some people may not see that one actually in application, but they exist. So we use any water sources that we have, like a pond, like a lake, and other ones, and then we connect our heat pump and then we take advantage. Or the ground source heat pump. The ground source heat pump is that digging the ground, it can be from 200 feet to 600 feet boreholes, and then we take the advantage of the heat underground. I mean, in downtown Toronto, I worked on a couple of projects. The downtown ground, if you go 600 feet down, it's around 8 to 10 degrees Celsius all year around. So now you can think of that temperature difference, 8 to 10 degree all year around underground versus the air temperature in summer goes to over 30 degrees Celsius. In winter goes down to minus, let's say 10, minus 20 degrees Celsius actually. So that's another source. These days, because the heat pumps that we have in the market, if you look at the capital cost, it's better that we use a backup or a hybrid heat pumps as well. Means that we need some kind of a backup system, either a resistive heating or a combustion heating, that I will speak about that one. The last one that mainly I saw it in an industrial application, they are absorption heat pumps, but again, they are also good to be considered for our projects actually. How a heat pump works. If we are in a summer season, what is happening is that actually the heat in the summer season, it will be extracted by this coil that we have inside actually. So this is going to be this is going to be our evaporator, which takes the heat from inside our buildings and then transfer it to this magic component of the cycle, reversing valve, which the air conditioning, they don't have only this one. So that's the only difference between an air conditioning system and a heat pump, is that the heat pumps, they have reversing valve, and then they take that heat to the condensing unit and then dump it outside actually. So this is the flow of heat that we see in the summer. In a winter season, it's opposite, means that it's taking the heat from outdoor air, whatever amount of heat that exists, and then take it to the reversing valve and compressor, and then bring it to inside or indoor environment and then heating up. So this is the flow of heat actually in either summer or in winter season actually. And then based on that, we can say that where is the source and where is the sink for a heat pump actually. As I talked about the different types of heat pumps that exist, one of them is water source heat pumps. Water source heat pumps actually are preferred, and they are better because water has higher heating capacity compared to air. So water has water can actually store energy 4 times more than air in itself. So that is why then we can transfer a larger amount of heat through this process or through this equipment that we want to install. The other benefit of the water source heat pump is that we don't need a defrost cycle actually, because in a winter season, the heat pumps, the air source heat pumps, they work, and then because of the humidity that might exist, then we need to defrost the cycle, which actually takes some energy to do that defrost, because the system shuts down itself, going through the mode of defrosting, and then come back actually. So it means that during that hour or that time, we don't have any heating and cooling. The other thing is that it uses energy. So that is not good actually. So it has higher efficiency. One reason is because of the high heating capacity of the water. The other one is that there are no defrost cycle and so on. Because of that, again, because of the water, the compressor works less actually. So it is good in different types of buildings. So if you have a project that your project is nearby water, and for environmental reasons, you're allowed to use that water, or you're allowed to connect your heat pump to that, consider this one, and that might be a good solution. I mean, it can be different solutions. The typical solutions for water source heat pumps are open loop systems or closed loop system, which the preferred one is the closed loop system, because in the open loop, you have the flow of the water directly from the stream of water that you have to your system, and then that is not actually good, because then you need a water treatment and actually. So the preferred system is a closed loop system. For a closed loop system, what is happening is that as you can see, the sink and the source, they connected to a water source, whatever system. It's a pond, it's a lake, it's a river, whatever it is actually. So then the heat is getting transferred to the heat pump that we have, and these systems that we have, basically they transfer the heat. Either if it's in a summer mode, means that the heat is going to the water actually. So this is the summer mode. And if it's a winter mode, then actually we want to take the heat in this direction from the water and then bring it to our systems actually. So there is a one, this is a closed loop, means that this loop actually that you see here, it works for itself, and then it's not taking any of the water from that source that is available to you actually. It can be a ground wells, it can be a lake, it can be a pond, and so on actually. The open source that you see here is that basically we take the water directly to our heat pump, and then we dump back actually, let's say if it's in the summer mode, we dump back the heated water to the lake and so on. So this is also good, but there are some environmental consideration, which, I mean, it doesn't allow us to do it in many places. So we should check for this one actually. But their COP of these water source heat pumps, they are good. They are higher than the air source heat pump, and also their efficiency, is much better. But let's look at the types of heat pump system that are available to us. It can be, I mean, these days, air source heat pump as a single split. This is a very common. It's a one unit. It can provide heating or cooling to one area, or it can be a multi-split system. So again, we have one condensing or one heat pump unit outside, and then we have different types of units, sealed, uh, ceiling beams or fan coils or fans like this. They can be installed, any of them, and connected. Or I mean, typical ones that we see, a package terminal heat pumps that we see in some hotels that they install that one. Sometimes they become noisy because everything is inside this unit actually. The other thing is that the rooftop units actually. So these days, if you're ordering a rooftop units, make sure that you order a rooftop unit with the heat pumps, or a heat pump rooftop units actually, because as I said, they just need to change the one of the equipments or one of the little equipments inside the cycle, and convert it to a reversing valve actually, and then that's it. It becomes a heat pump actually. So then instead of air conditioning, it becomes a heat pump, and then if you need a backup, again you can do that one. And the cost increase is very minimal if you order heat pump on these ones. The other one is a hybrid heat pumps, like these ones that you see here, and also ground source heat pumps that you see the pumps are connected, to the underground, that we have it, and then brings glycol, whatever, media that we have, bring it here and we use it. The most advanced version of the heat pumps, it changes its name and it's called variable refrigerant flow, or VRF. The concept is the same thing, but we will actually pipe the refrigerant to every zone that we want to bring heat, and then we add a fan coil or a ceiling beam or whatever system that we have, and then we use that one actually. So that's a VRF. I will speak a little bit about the VRF in more detail, similar to water source heat pump. So a VRF, variable refrigerant flow, it's a heat pump actually, and it can provide, heating or cooling to different zones by actually piping the refrigerant to those zones, and then install a system like a fan coil or ceiling beams, and then heat up or cool down those areas actually. The VRF system, again, the best is that to use it for multi-zone applications actually, and then it can be for different thermal profiles as well. One wants super hot, the other one wants the super cool environment. VRF can accommodate that one. And again, the main concept is that taking or transferring the heat from one to another place. So if it's in the summer season, means that from inside of the building to outside. If it's a winter season, from outside to inside, actually. We talked, really good about the heat pumps and say that these are the advantages, but the at the mild temperature, mild outdoor temperature, and if we are talking about air source heat pump, their COP in a mild temperature, let's say around up to 0 degrees Celsius, up to warmer summer season, their COP can be 3 to 4 actually. But then the performance actually drops in a very cold condition. So if you go to northern part of Ontario, which it's minus 25 and so on, then either we need to buy cold climate heat pumps actually, which they become expensive. If a typical heat pump is around $3, $4, $5, $6,000, their price might be $10,000, $12,000 depending on the size, and their performance actually goes around 1 to 2. So their COP goes pretty low actually. So then if we go back to that comparison, then it becomes comparable to a combustion unit systems actually. There are different types of controls. If we have a hybrid heat pumps, then because these days we need to survive, I would say, in a cold winter season. So then a hybrid system is necessary to have it, or invest in a cold climate heat pumps, either of them. These days, the hybrid system is more popular, so means that it's different types of controls available depending on control strategy. That system shuts down the heat pump and turn on the auxiliary or the backup system that we have for the heating, and then it runs that one until the control decides again to go back actually. Again, still heat pump has a lower carbon emission. The cost can be optimized through a fuel switching actually, so it's a good one. And then it's reliable, resilient, and it works. And they offer a lot of good flexibility for retrofits, and also there are incentive actually. So depending on the area, on the region, there are incentives available for that one. But let's speak a little bit about the control strategy and control options for hybrid systems, because now we can just have the control based on the temperature. Switch over means that either we have a set point, and based on if the heat pump owner, they want a warmer, for example, environment, let's say 24 degrees Celsius, 25 degrees Celsius, and outside, let's say, is -5, -10, maybe it's better that to switch from heat pump to the backup system or to the hybrid system that we have. It might be based on a load control actually. These days smart thermostat, they can provide that one actually based on the use and the load profile, and they know that one. And these smart thermostats or learning thermostats, they can even do a preheating and pre-cooling, which then they see that at night the temperature will drop to, let's say, -20. So they heat up well in advance when the outside still is not that super cold. So they take the heat from outdoor air, they bring it in, they heat up more inside the building, and then there will be a smoother drop in the temperature. So then the heat pump does not need to work, or the hybrid system does not work. The other way is that going to the BAS, building automation system and advanced control actually, or the most advanced one can be time of use, cost base, and so on. VRF also, if we want to do the zoning for the VRF, it's the same thing. So the highlight is that having the right control strategy can optimize our utility costs, reduce GHG emission, and improve the comfort. So these are the goals of having the right strategy, the best strategy or control system for a hybrid or a VRF system actually. So if we have a BAS, And then if we integrate it with outdoor temperature, pricing of the electricity and other fuel that we use, and also the occupancy profile, then the BAS can decide, smart way, and then we can benefit from that one. Or we can have it demand limiting to avoid peak utility charges. Again, I mean, during the peak hours these days, in a very cold hours, we see the peak actually in our electricity. So maybe that's better we switch to our hybrid system that we have, or coordinating with the heat recovery chiller and the loops that I will later on speak about that one. And then, the best is that to optimize, the BAS system based on all these parameters that we talked about it. So the benefits of a smart controlled, first, economic, is that, we want to reduce our cost or, energy cost. The other one is the GHG. The next one is operation. So operation means that giving a better occupancy comfort and also keeping our equipments to be used for a longer period of time, and being resilient in extreme weather actually. Now I want to switch the topic.
Sorry,
Sure.
I just want to address two questions in the chat.
Sure.
Yeah, there's a question from Dave that says, would you go with the ground source heat pump or an air source heat pump, considering that land is not an issue for a single detached home?
Yeah, I mean, ground source heat pump is much, much better, is more reliable than the air source heat pump, because we have a fluctuation of almost 60 degrees Celsius from winter to summer season actually for air. But the ground, if you go deep, it's always constant temperature. So we can design, and also the ground has higher heat conductivity, similar to what I discussed actually for comparing water to air. Ground also has higher heating capacity compared to air. So for sure, if you can afford it, if the project allows the capital cost, and also you have enough land, ground source heat pump is a better solution.
Perfect. And then we have one more question from Matthew. Is there evidence that heat pumps are going to last longer and cost less to own and maintain than conventional condensing gas furnaces?
I mean, yes, for sure. There are, many studies that, you can go to scientific papers and journals and articles that they studied the life cycle of both of these systems, and they compared, because, one of the reasons that combustion, inside the combustion chamber, we have much, much, much higher temperature, and then because of condensation and other reasons, then the equipment degrades faster actually. So that's one of the reasons. And then combustion chamber or combustion environment is a harsh environment actually. So any metals, anything inside, they last less, compared to the heat pump, which it has a compressor. But there are studies. I don't have those data available actually to show you today.
Thank you.
No worries. So let's switch the topic and talk about heat recovery. I mean, if you go to ASHRAE handbook, so it's a big, big topic about heat recovery. And the main point is that wherever that we have waste heat, wherever that we have heat, let's take it and let's use it, because somewhere else we spend energy, we spend money for that heat actually. So it didn't come for free actually. So we have different types of heat recovery, air to air, like a plate heat exchanger, wheel ones that you see here down here, or run around loops and so on actually. We have a water side heat recoveries like a heat recovery chillers, condenser water loops, and so on. The VRF systems also, they come with a heat recovery as well, which I have a slide, I will speak about that one. And also the industrial applications, they have a lot of waste heat. So it's better that they use that one. If you have a compressed air system, your air compressor is the main source of the waste heat. And that waste heat actually can be directed to your boiler incoming air actually. So basically you can preheat of the air that going to the combustion of a boiler or if your furnace from your air compressor system that you have it. So that's the waste, and then we need to recover. Just calculating, ducting, and then that's it. Or data centers. I mean, data centers, they need to stay at a certain temperature, let's say 18 degrees Celsius, 20 degrees Celsius, and a certain relative humidity. So then a lot of waste heat. Why not using that? Why we just take it to our chiller and then chiller dump it outside? So I mean, let's use that heat if we can. So combining a data center with another application, I mean, this is funny, but putting a swimming pool beside it, you can provide the entire heat that you need for the swimming pool. I know that it's not a safe thing and secure, but that might be a solution actually. So it's better that we consider these ones. So typical efficiency ranges for heat recovery. If you have a plate heat recovery, a plate heat exchanger, it can be 50 to 70%. Energy recovery wheels 65 to 85. Run around loops is less efficient, 40 to 60. Um, Heat recovery chillers, they have a COP of 6 to 8. And then VRF with heat recovery, you can expect 20 to 40% more efficiency on the VRF systems actually. Examples of these heat recovery, I mean, for office building, energy recovery ventilator. So for office building, for residential building, this is really good. You can increase or you can decrease your energy use from 20 to 30%. In a hospital, heat recovery chillers is, to me, it's a must have. It's not something that is good to have. It today is a must because that technology is available to us. I mean, it has a cost to install that one, but the saving is huge. The saving can be more than $100,000 per year. For a multi-family residential VRF recovery, that can be. And then on top of these, energy, which is actual cost reduction for us, it's emission reduction. This is emission reduction using any heat recovery is around 20 to 40% actually. So if we use an ERV as an example, and if you have a 50,000 CFM, and let's assume ERV has a 60% efficiency with a 2,000 million BTU annual heating load. So then the recovery, it can going to be a lot actually. And then this is going to be around $14,000 to $20,000 fuel saving every year actually. So, I mean, there are many examples, I mean, and we should benefit for that one. I want to touch on the VRF heat pump. So a typical VRF is that either, I mean, this is a very typical one that you see here. For every zone, we install an outdoor unit actually. So each of these outdoor units connected to one of the fan coils, for example, or the ceiling beams that we have inside. And then depending on the thermostat, the user comfort, they provide either heating or cooling. We can have a branch controller. So in the branch controller, we just install one unit, and then we this branch controller, based on the thermostat setting, it decides to send heating or cooling, refrigerants actually. But then the thing is that maybe this area, this area requires cooling, means that the heat needs to be taken out. So instead of taking out the heat and then take it to the outdoor unit, why not taking out the heat to the branch controller and then branch controller bring it back to other environment? Because this is a waste heat that needs to be removed from, let's say, these two areas, and now that heat can be dumped in the other. And if extra heat is necessary, then the outdoor unit starts to work and then bring extra heating that is necessary. So the heat pump these days also can be actually designed to have a heat recovery. It's just a design. You don't need any extra. If you have a one outdoor unit and then branch controller, the branch controller and the proper settings can accommodate that one. It just takes the heat to the branch controller and then actually from those areas that they need cooling and then dump that heat to the areas that they require heating at the same time. So again, that's a good one. But this is for the cases that we need simultaneous heating and cooling, or at the same time heating and cooling actually. Now I want to just focus on integrating these two great technologies together actually. So integrating heat pumps and heat recovery. It can be combined or integrated with any combustion system, like a boiler, like a furnace, or even the solar thermal systems, actually, we need to have a proper control for sure. And then the proper control, as we discussed, can be based on the load, can be based on the temperature, can be based on emissions, or it can be based on the rate that we have actually. And then we can repurpose the space heating and then use those extra waste heat for preheating, for domestic hot water, and so on. What is the outcome of integrating these two, increasing the efficiency, reducing the operating costs, lowering the GHG emissions actually, and then we are going to have year-round efficiency, lower utility bills, and a better redundancy in our system. One thing to consider is that if we integrate these two, our equipment also size will go down. Means that we need a smaller size, which means equals to less capital cost actually. We can benefit a better indoor air quality. We reduce the HVAC load and the cost that we discussed actually, and this is ideal for almost every type of building, residential, commercial, and even institutional buildings actually. So our goal is that to maximize energy saving, and then that will provide us more benefit. In the final slides that I have for you, I want to just present to you some real case studies that exist in our world, in a real world, and we want to take a look at that one. The first one that I have is the exhaust heat pumps actually. So Dantec actually, they installed on a large facilities like a hospital, so very large commercial buildings actually. So on the exhaust, based on the code, we cannot take that heat actually to any villas or anything else actually, because they are coming from washroom, they are coming from shower room, change rooms, and we are not allowed to, based on the standard or codes, we are not allowed. So we need to dump it out. But they are heated up actually already. So if we install a heat pump on that one, then either we can take back, so the heat pump takes that heat actually, and then run its process, and then either use it for the cooling of the building actually, or we can actually use it for domestic hot water. So this is a one application, and this is good. In this slide, I show a conventional common heating and cooling system that we have. So we have a boiler, and then we have a chiller, and then the chiller connected to a cooling tower, and then the exhaust from the washroom, change rooms, and shower rooms, it goes directly out. So it goes directly out. And nobody take advantage of that one actually. And the point is that we cannot bring it back and either mix it with the fresh air, or we cannot put a wheel on that one because it's a dirty air, I would say. So for that reason, typical application is that they put a fan up and then they just take it out to atmosphere. That's it. But we can install a heat pump or some kind of a exchanging system in here, and then that exchange system actually that can take the heat and then convert it to the cooling, for example, and then send it to the chiller or cooling system that we have. And also the size of these equipments will go low, becomes a smaller. The boiler, the chiller, and the cooling tower, because now we have an extra source that is running all the time actually, because these exhaust fans, they need to work. So then this is a year round, and we can take advantage. I encourage that if you have such a thing, go and check these kind of applications. So this is a good integration of a heat pump and a heat recovery system. The second case study that I have is the heat pump combined with an energy recovery ventilation or ventilator actually. So basically, typically we put a energy recovery ventilator, and then we mix that one air and back. But in this case, instead of taking that air, let's send that air to a heat pump, either from heat pipe, energy wheel, fixed plate, or run around, coils, whatever that we have, and then send it to a heat pump, and let's the heat pump take that and then convert it to what do we want actually. In this
Sorry,
example,
I just
yes,
have
sure,
one question. Sorry.
sure, sure.
Yeah. Go ahead, Sridhar.
Yeah, in the previous slide, so the chiller is a heat pump, a heat recovery chiller or normal chiller?
It's a normal chiller, but we can consider different types of chillers as well. So I mean, one thing is that if you are designing, then it can be, a complex design actually, depending on the building actually by itself.
Yeah, in the perspective of operation and maintenance, so what do you suggest? Is it not more complex for the building operators to operate and the system with increased complexity?
For sure, it increases the complexity, but I would say that training and proper BAS setup can cover everything actually. And I mean, we are moving to that era that now we are going to have buildings with more than one heating system and one cooling system. So I mean, it's coming because one thing we need to consider, almost every equipment that we have, I mean, in our in our hand, their efficiency is at the peak, at the max, 80% efficient, 90% efficient, 92% efficient. So, or COP of 2, COP of 4. So means that now we need to combine two systems or integrate 2 to 3 systems. So for sure, it brings complexity, but proper training and BAS can take, uh, cover those things actually.
Yeah, could you please explain here the heat rejected is sending out in the boiler circuit so that it can be used for heating. But here the heat recovered from the exhaust fan is connected to the chiller in the cooling side, right?
Yeah.
Could you
So
explain that?
yeah, so basically we condition, I mean, the word condition, I don't like it. Basically, what we have from exhaust fan, let's say this is a winter season, in exhaust fan we have a heated air that is going through our exhaust fan. So before doing that, we recover that waste heat, but the wording that in our mechanical engineering word, we call it air conditioning. So the heat pump basically condition that one and then take that one and then convert it to whatever that we wanted. But remember, it's converted to a cooling. I mean, this is a typical example for a building that has a data center, and data center needs to run 24/7, it doesn't matter. Or if it's a hospital. So these are the example for this application that I'm showing. And now it can send that cooled or conditioned uh, refrigerant, I would say, back to the system that we have it. And basically, this is some kind of a free cooling that we got it actually.
Yeah, my question is that one. So we are recovering the heat, how it is used for cooling here in the chiller.
It's not going directly to the chiller, it's going to the distribution. Maybe the piping diagram that we have, it means that it goes to the sources of the cooling and then, but if you have a heat recovery chiller, then you are right. So we don't need that conditioning up there. Then a heat recovery chiller can take advantage of that one. Yeah, either of them, either putting a heat pump up there and then take it down and then bring it to the chilled water distribution that you have it, or as you said, install a heat recovery chiller and then taking the heat to the heat recovery chiller and then use that one, either of these applications.
We also have one more question from Christina.
Okay, yeah, we have only 6 minutes. I want to
Yeah,
finish it. So yeah, sure.
I'll be quick. Thank you.
Sure. No worries.
I have a scope of work that I'm writing now, and in fact, we do have a washroom vent that needs to be corrected, right? So the washroom vents need to be direct vented out. But I thought I caught wind of you saying, no pun intended, that the air can be reutilized for that, even though it should be exhausted as quote unquote dirty air. But I feel like you said it would go into air conditioning. I just want you to repeat that if you could.
Yeah, I mean, the idea is that we cannot install a plate heat exchanger. We cannot install a wheel, energy or heat recovery wheel for the exhaust fan. We are not allowed to do that one. But we can install some kind of a heat recovery chiller, or an air conditioning system, which basically this is taking advantage of the heat. So this is the heat pump that takes the heat actually from the exhaust air and then convert it to the cooling for us and then send it to the cooling system that you have. So in your application, if you have simultaneous need of cooling and heating, then you might consider this one actually. If not, if you need
Yes.
during the heating season, you need heating, so then you
Yes.
can consider heat pumps that takes the
Mhm.
heat and then
Mhm.
pump that heat back actually to you.
Right. Okay,
So-
because this building is historic and does have warm and hot spots all the time. And I
Yeah,
did notice one of your drawings on the previous riser kind of diagram that showed a machinery piece that takes the heat and cools it and throws it back in before it goes to the outside machinery. So,
yeah, yeah.
okay, thank you. You
That's
answered
good.
that.
No worries, no worries, no worries. So we were discussing about the second, which is similar to the first one, but this is maybe for smaller buildings. So instead of having those recovery systems, let's keep them, but let's add a heat pump. Let's not bring it back. So either it's a wheel or it's a heat pipe or it's a heat exchanger or it's a coil. Let's take that extra heat and then recover it through a heat pump. And then by doing, because the heat pump, they basically they transfer the heat and then they actually increase the efficiency for us. So maybe that's another application that we can think of. The other one is the heat recovery heat pump with and without heat recovery. So this is a very deep, detailed study. I really loved it. If you have a time, just I put the link or the name of it, just search it, take that study in a typical application that we might not need to add a heat recovery ventilator. So we say that we don't need it, and then we have a heat pump. But if we install a heat pump, I mean, then this graph, it shows everything to us actually, depending on the zone. So let's say Toronto area, it's around 3,500. So this is the area for Toronto. Or if we go to colder climate, let's say 4,000 heating degree days, then these two graphs or these two lines that you see showing us heat pump with heat recovery ventilator, heat pump without. And then you see that this is the annual energy or heating energy that is needed actually. So this is it. This is with heat recovery. This is without. So we are talking around, let's say, 90 kilowatt hour per square meter versus 150 kilowatt hour per square meter. So that's the amount of heat that recovered by our ventilator, and then the heat pump took the advantage of that one actually. So again, we don't have that much time to go through this one. Again, this shows for different cities actually across Canada, and then the use the annual heating energy use reduction. This is the range for different cities that we have. So this is for Toronto, for example, and then you see our heating demand or the heating energy use will go down. The last case study that I want to show you that, again, for the rooftop units, it is this: if you order a rooftop unit, please order a rooftop unit that has a heat pump in it actually. Heat pump plus the energy recovery again. So I'm adding to that one. So energy recovery and heat pump rooftop unit. Then you see if we have a natural gas burning rooftop, then let's say in this real example, it's around 850,000 kilo BTU of natural gas, 500,000 electricity, 500,000 kilo BTU of electricity. So 1.3 million kilo BTU, that's the total energy. If we install a heat pump or rooftop unit, for sure, zero natural gas, then the electricity use will go higher. It becomes 800,000 kilo BTU. That's going to be the only energy that we need. If we install a heat pump rooftop unit with energy recovery, then that 800 goes down to 730,000, and then that's going to be much less, energy use. So again, investing on our heat pump and then adding energy recovery to that one, then we can benefit to that actually. And then this is the profile for a typical days between, let's say, February, and then this is a typical load, differences between each of these three systems that for sure, the difference between no energy recovery and energy recovery heat pump RTUs is minimal comparing to the natural gas burning one. But again, it's something that then if you multiply it by, let's say, 10 years, 20 years, then it becomes a lot bigger value, especially in areas like us that electricity is not, cheap, so it's expensive. So in summary, combining of these technologies, it will increase the strengths, and I'm sure, as we discussed, brings complexity, but we need proper training, proper BAS setting, but it's really good actually. It provides energy saving and GHG reduction for us. The heat recovery achieves, as I showed you, between 50 to 80% energy recovery. It will brings us flexibility for climates and different building type, but having a smart control, it will help us to benefit more from these ones, and also reducing the cost and also the GHG emission. The hybrid systems or integrated hybrid systems, I would say they can lower our operational cost and actually lower our emission and also increase the efficiency. But some more questions, just for discussions, what type of this system fits for your building? What are the challenges? What are, in implementation, in design, in operation? Again, needs to be taught in advance and planned for that one. And then looking always the life cycle cost versus the carbon emissions versus the climate resilience, which of them most matters, or we need to combine all of them together actually. I have three more slides that there are training incentive from ISO. So achieving net zero buildings, ISO 50001, HVAC optimization in high performance building, certified energy managers, certified measurement and verification professionals, they can receive an incentive for the training. The amount of the savings is available on ISO website, either $500 per day, or for a course of building operators, $2,250 or $2,500 for CEM. And then there are, more live training. Please check the calendar. And there is a one post-webinar intake form. Please fill it in. It will help us for the next, webinar that we are preparing actually.
And if you go to the second last slide, next slide after
Sure,
this.
go ahead. That's
next slide after this. Sorry.
Oh, this one. Okay, sure.
Yeah.
Is that
So
this one?
So this is the survey that you'll be receiving soon. If everyone can please just fill out the survey, it takes like 2 or 3 minutes. Just add your thoughts or comments on today's session, and it really helps us a lot for preparing for our other sessions. And on the next slide, you'll see our Save on Energy, the website, training and support link, which I've added in the chat, and then our LinkedIn, Facebook, and Twitter pages as well.
Yeah. Sorry for running 3 minutes late, but at least we covered a couple of questions, and also we covered the entire material. Thanks for listening.
Yeah. Thank you, everyone.
Thank you. Thank you,
everyone. Take care.